This video is an introduction to mathematical induction. I found that a lot of students struggle with the idea of mathematical induction. So in this video, what I'm going to do is explain how it works and then use a really easy example to put it into practice. So let's start off by thinking about what we might want to be doing. Mathematical induction is used to prove a statement, which is usually a statement that holds for many values of n. For example, some statement that holds for all n bigger than or equal to 1. So let's think of that as our main goal. Our goal is to prove s sub n, which is just going to represent our statement, s for statement, for all n bigger than or equal to 1. Okay, so before we get into how to actually do a proof by induction, let's think about a few things. I'm going to write down some statements that I claim I have already proven to you, and I want to see if you're convinced that the statement will always hold. So let's start with the first thing. S1 is true. If I prove to you that S1 is true, you're only going to be convinced that the statement is true when n equals 1. Fair enough, because that's all I've shown. If S1 is true, then S2 is true. If I'm able to prove to you that if S1 is true, then it must follow that S2 is true, you're going to say, okay, hold on. I know that you've shown me if S1 is true, then S2 is true, but you also showed me that S1 was true. So you can conclude that you know S2 is also true. And you'd be happy. So far, you're happy that the statement holds for n equals 1 and for n equals 2. Let's see what else I tell you. If S2 is true, then S3 is true. So let's say now I'm able to prove to you that if S2 is true, then S3 has to be true. Well, from the previous step, you already knew that S2 was true, so you would conclude happily that S3 is also true. And I can continue like this. If S3 is true, then S4 is true. Again, if I prove to you that if S3 is true, then S4 is true, you're going to conclude that S4 is also true because we started off knowing that S1 was true, and we used a domino effect to say, okay, that means S2 is true, then S3 is true, now S4 is true. But this looks like a lot of work. I have to keep going, and I have to again prove to you that if S4 is true, then S5 is true. And then once I've done that, I have to again prove to you that if S5 is true, then S6 is true. That's too much work. So what we want to do is cut down all that work and do all of that in only one step. And that's the beauty of mathematical induction. So instead of doing this many times, in fact, we'd have to keep on going to infinity, what we're going to do is replace this entire block by a single statement. If Sk is true for some k bigger than or equal to 1, then Sk plus 1 is true. Isn't that great? I can do this once. If I prove to you this statement in red, if Sk is true for some k, then Sk plus 1 must be true. What you get from that one statement is all of these statements. So let's say I only prove two things for you. First, I prove that S1 is true. You're happy that the statement is true just for n equals 1. And then I prove to you this statement in red. If Sk is true for some k, then Sk plus 1 is true. Will you be satisfied that it has to be true for all n? Let's think about it. You are already satisfied that it's true for n equals 1. When you think about n equals 2, you say, well, okay, all I have to do is say it was true for k equal to 1. So now I know by the red statement that it's true for k plus 1, which is 2. And again, you loop in. You say, now I know it's true for 2, so it must be true for 3. And you keep going, and it's true for all n bigger than or equal to 1. So if that makes sense, let's do an example. Remember our goal. Our goal is to be able to prove two things. The first thing is this piece, and the second thing is this piece. So what I'm going to do is write down those two pieces to remind us of what we need to do. So let's recap. If I'm going to prove to you that the statement S sub n is true for all n bigger than or equal to 1, then I have to do two things. The first thing is to show that it's true for the first value of n, in this case, n equal to 1. The second thing that I need to do is to prove to you that if the statement is true for some value n equal to k, then it must also be true for the next value, n equal to k plus 1. So those are the two things that I need to accomplish. This first one is called the basis. This second one is actually the trickier part, and that's called the inductive step. So to show you how this works in practice, I've chosen a really easy example so that if this is the first time you've seen mathematical induction, it should be really clear.
Alright, welcome back to some logic. Today we're going to be doing mathematical induction. So, what is mathematical induction? It is a proof technique to say that if we know this first thing is true, and if we pick some random step, the step above it is true, then everything must be true. So, imagine climbing a ladder, and we're going up this house. It's a little ladder, and what we want to do is we want to say, okay, this ladder is infinite. That's what we want to say. You know, you can keep climbing it as long as you want. It doesn't matter how high you go, you can keep climbing on it. There's two things we have to check. One, can you get on the ladder? And two, if you're somewhere on the ladder, there's going to be another step. So if you're on some point in the ladder, you should be able to step up at least one step. And it doesn't matter where that step is, you just should be able to step up. And if we have both of these things, we know you can get on it, and for any k step, you can get to the k plus 1th step, or k plus 1st step, then you should be able to get as far as you want. And this is what I have in words here as the base case, getting on the ladder, the inductive step, moving up a step, and the conclusion. This is mathematical induction. So I'll give you these formal definitions. A base case is something that we say, oh, it's the base. This is the beginning. We need to get it going. So we need to show that something is true for the first value. And the inductive step is saying, well, hey, let's just suppose we have this step, and let's just assume it's true. Then is it going to be true for the next step? And if we can prove that it is going to be true for the next step, because our first step is true, we can say, oh, hey, well, what if this arbitrary step we picked is actually the first step? Then the second step is true. But then that arbitrary step can be the second step, and then the third step would be true, and so on and so forth until we've proven everything.
In this film, I will explain the idea behind induction proofs using dominoes. Imagine you have an endless array of dominoes. You're going to push one of them. How can you be sure that all the dominoes will fall? Well, the first thing you need to be sure of is that the dominoes are close enough so that if one domino falls, the next one will fall too. Because otherwise the fall will stop somewhere. The second thing you need to be sure of is that the domino you push is the first one. Otherwise, some dominoes will remain standing. If you're sure that both of these conditions are met, then you can be sure that all the infinite number of dominoes will fall. And an induction proof works in a similar way. First, you show that if the statement is true for one integer, then it is also true for the next. Then you show that the statement is true for the first integer. Having done this, you can be sure that the statement is true for all positive integers, just as you can be sure that all dominoes will fall.
Mathematical induction, using the analogy of the ladder climbing robot. The principle of mathematical induction is a method of proving statements by first of all showing it can be true for n equals 1, and then by showing that if you assume the statement is true for n equals k, then you can prove it is true for n equals k plus 1. If those two statements are true, then the statement is true for all positive integers n. I think this works a bit like a ladder climbing robot. What you're trying to prove is the ladder. You need to get the robot onto the bottom rung of the ladder, that's n equals 1, but you also need to make sure you can go from one step to the next, and then you're ready to go. Because if you can get the robot onto the bottom step of the ladder, then you got it onto step n equals 1. But if you can then show it can go from any step k to step k plus 1, you can make it go from rung 1 up to rung 2, from rung 2 up to rung 3, rung 3 up to rung 4. And you can keep on climbing to infinity, but not beyond. So when we're trying to prove something by mathematical induction, there's 4 things we need to do. We need to state what our aim is, what it is we're trying to prove. That's the ladder. Then we need to get onto the ladder, normally at the bottom rung, n equals 1. Then we have the awkward bit of showing how to go from any one rung to the next one. And then you start climbing. So these 4 things are defined. The words we use to describe them when doing induction are a proposition, what it is we're trying to prove. We have our base case, the bottom rung of the ladder where we start from. Our inductive step, knowing how we can go from one step to the next. And this is normally the really difficult bit. And then finally a conclusion, which actually starts to get a bit repetitive because it's almost always something very similar. Because we're just stating not only what we've proved, but why we know we've proved it.